Functions are fundamental to calculus as numbers are to algebra and angles are to trigonometry. Today in this video, we will try to get a very firm grip on the concept of functions. I must warn you that there are a lot of abstract concepts on your way, and I am assuming that all of you have a very rudimentary understanding about the subject of sets, and I am talking about functions in real numbers. Functions in complex numbers, we will do a separate set of videos later. We will start off with a very quick, short introduction about functions in a very unsophisticated street lingo. Here we go. Want to master calculus? Start with the basics. What are functions? In street lingo, functions are like machines or engines which take an input value, works on it, transforms it, and throws out an output value. The machine is also very dumb. It understands the input only if the input is in the machine's domain. If you input something that is not in the domain of the machine, it could actually blow up, as we shall see shortly. The collection of all possible outputs the machine can throw out is called its range. Here are a few examples. Exponential function. This machine takes an input and raises the input to the power of e, the Euler's number, which is a special irrational number, 2.71828 and so on. Squaring function, as the name suggests, the machine squares the input. Next is natural log function. The machine throws out the value of natural log, which is logarithm of a number, to base e, the Euler's number. Oopsie daisy, oh my god, the machine didn't like the input 0, so it blew up. Be careful while choosing your input. Don't feed anything that the machine doesn't like or understand or outside its domain. It is going to be messy. Next is a sine function. The output is the trigonometric sine value of the input. This function is a very nice one. It's very patient. It takes in all and any junk from negative infinity to positive infinity. But the output in real numbers is restricted to values within +1 and -1. You can represent functions as graphs in Cartesian coordinates in real numbers. We shall be using the graphical representations frequently in our discussions. Another tool that is very vital is the concept of intervals. It is often useful to evaluate a function across an interval of input values. There are two kinds of intervals, open interval and closed interval. In an open interval, the starting and end points are not included in evaluating the function. The mathematical notation for the open interval is a pair of curved brackets. On the other hand, in a closed interval, the starting and end points are included and written with a pair of square brackets. As an example, I'll describe the sine function in the interval 0 and pi. Based on our definition of open and closed intervals, we can make the following two statements. First one, the open interval statement. Sin x is greater than 0 and less than or equal to 1 in the open interval 0 and pi. So this is our open interval statement. Next is the closed interval statement. Sin x is greater than or equal to 0 and less than or equal to 1 in the closed interval 0 and pi. Notice that we have added equal to 0 to include the fact that sine 0 is equal to 0. With this quick sort of non-mathematical introduction to functions, we shall get a little more serious in life and discuss functions in a rigorous format next. Okay, after the non-technical introduction to the concept of functions, things are going to get a little more formal. First, I'm going to read out the mathematically rigorous definition of a function. The definition goes like this. A function f from a set D to another set E is a correspondence that assigns the element x in set D to exactly one value y in set E. Sounds confusing? Let me break it down for you in this video. Let's say we have two sets, set D and set E, and the elements of set D are X, B, U and V, and let F be the correspondence, that is the function F. Let's call the correspondence as function F. Now the function F corresponds X to an element F of X in set E, B to F of B in set E, but it assigns U and V to F of U and F of V, but represented by a single element. That is, both U and V correspond to a single element in set E. Let me give you a very real world example. Let's say F is a squaring function. Let X be equals 3. That means X corresponds to F of X, 3 square, that is 9. Let's say B equals 6. B corresponds to an element F of B in set E, that means 6 square is 36. And let us say U is 4 and V is minus 4. Now F being a squaring function corresponds both plus 4 and minus 4 to a single element in set E, that is plus 4 square is 16, minus 4 square is also 16. So U and V correspond to a single element, that is the function F corresponds U and V to a single element 16 in set E. This situation is perfectly acceptable and is consistent with the definition of functions which I have written there. That is because it is corresponding an element in set D to a single element, that is exactly one element Y in set E. So it is perfectly consistent and acceptable. Let's look at another situation. Let's say the function F corresponds an element in set D, that is X, to two different elements in set E. This is not acceptable. This is not acceptable as per the definition of the function, because it has to correspond exactly to one element in set E, whereas here in this case it is corresponding, that is the function is corresponding element X to two different elements in set E. Not acceptable. That is not a function. Now, in our earlier video I said functions are like engines, machines. They do a mathematical operation on the input and spits out an output. That's a very colloquial view of the function, because functions need not be mathematical operation. It need not be a squaring function. It need not be a logarithmic function. It need not be a sine function. It need not be a mathematical operation at all. Let's say the set D has, let's say, a book by Douglas Adams, that is The Hitchhiker's Guide to Galaxy. The function F counts the number of pages. So the function F corresponds the Hitchhiker's Guide to Galaxy in set D to 224. That is the number of pages in set E. Therefore, the function F is a logical operation. That is, it is counting the number of pages in a book. Or let's say the set D contains a red dot. The RGB value of the red dot is 25500. Okay? Don't worry about RGB values now. Just listen. The red dot has an RGB value of 25500. And the function F corresponds the red dot to a blue dot in set E with RGB value 00255. So the function here changes the color of the input from red to blue. Next, we shall see some more definitions. These are all jargons. You need to remember these jargons if you want a place in mathematics high table, unfortunately. But once you get used to them, you will be using them like a pro. Okay, next we will see two more definitions. The elements of set D are called the arguments of the function F, and the elements of set E are called the values of the function F. The arguments are called the independent variables, and the values are called the image of arguments under F. The next definition is the definition of domain and range of a function. The set D is called the domain of the function, and the subset R of the set E containing all possible values of X under the function F is called the range of the function. Not clear? We'll have graphs to our rescue.
Hello everyone, I'm Venkatesh. I'm an experienced maths and physics tutor. I mentor university students from all over the world.
Before we proceed, I'm going to give you a very crude introduction to how to calculate maxima and minimum points. It's going to be a very crude introduction. I'm not going to prove anything. I'm only going to list out the method that is used for the calculation. Let's say we have a function y equals f of x. To start with, you take the first derivative. At maximum and minimum points, the first derivative will be equal to 0. That is, the slope of the function will be 0 at maximum and minimum points. I am not going to prove you anything. We will have a detailed discussion of maximum, minimum, functions, limits, derivatives, integrals, antiderivatives in our calculus videos. This is just to calculate the maximum, minimum points for this function. That's all. So dy by dx, the slope of the function is 0 at maximum, minimum points. Then you will get an equation. You have to solve. You will get a set of solutions. Then you take the second derivative, that is d square y by dx square. Now, at the points where d square y by dx square is negative, that is, you apply the solutions to the second derivative, and if it is negative, then the point is maximum. And when you apply the solutions here, if the second derivative is positive, that point is a minimum point. Remember that the function can have multiple maxima, multiple minima. Then you can find the local maxima, minima within a certain interval that you can do. Or the function might have only one global maximum, one global minimum. Or the function may not have any maxima, any minima. All the three are possible. Okay, you should have that in mind. So with this in mind, let's go to the main calculations. So here are the calculations. Our function f equals a multiplied by cos bt minus a cos 3bt. I am going to differentiate f with respect to bt. But instead of writing df by dbt, I am going to write bt as some x. Let me call this as x. Okay, just to simplify things. So, f equals a multiplied by cos x minus small a is 1 divided by 3 cos 3x. Okay, now let us take the first derivative, that is df by dx. A being a constant doesn't bother us. Now cos x, the derivative of cos x is minus sin x. Then the derivative of cos 3x is minus sin 3x. Don't forget the chain rule, multiplied by 3. Multiplied by the derivative of 3x. Derivative of 3x is just 3. Okay, so this simplifies to a multiplied by, you have minus of minus plus, you have this 3 and this 3 will cancel. Right? So you have sin 3x minus sin x. And we have to set df by dx equals 0 and solve for x. Which implies, since a is not equal to 0, as per definition a is not equal to 0, therefore we can write sin 3x minus sin x equals 0. Okay, now we already know the solution for this. The solutions are x equals 0 and plus or minus 5 by 4. Okay, now let us take the second derivative. So d square f by dx square. So df by dx is sin 3x minus sin x. Sin 3x, the derivative of sin is cos, therefore this will be cos 3x multiplied by 3. Minus sin x is cos x. Derivative of sin x is cos x. Okay, so this will give me 3 times cos 3x minus cos x. Okay, now first let us apply x equals 0. D square f divided by dx square at x equals 0. So you have 3 cos 0, cos 0 is 1. So 3 minus 1. So it is 3 minus 1 equals 2, which is positive. Therefore, f is minimum at x equals pt equals 0. Next, let us apply x equals plus or minus pi by 4. I done a space, I won't just rub this form, okay? Okay, so we have to apply x equals pi by 4 here. So cos 3 multiplied by pi by 4. Cos 3 pi by 4. Then cos x, that is cos pi by 4. Cos 3 pi by 4 is negative 1 divided by square root of 2. Minus cos pi by 4 is 1 divided by square root of 2. This is clearly negative. So, okay, now let us go to plus. That is d square f by dx square at x equals minus pi by 4. So we will have cos minus 3 pi by 4 minus cos minus pi by 4. Remember, cos of minus x is nothing but cos x. Therefore, this two will be equal because cos minus 3 pi by 4 is equal to cos 3 pi by 4. Similarly, cos of minus pi by 4 equals cos pi by 4. So this will also give you the same. Therefore, at x equals plus or minus pi by 4, d square f by dx square is negative. Therefore, at x equals plus or minus pi by 4, the function f is at maximum. Okay, so in the graph which you had seen earlier, the maximum points were minus pi by 4 and pi by 4, and the minimum point was at 0. So that's the calculation of maximum minimum points for our question number 10 of trigonometry. Thanks for watching. Welcome to question number 17 of our series on trigonometry worked out examples. Today the whiteboard is empty. I have not written down the question. That is because before we go to question number 17, I thought it's better to explain what is rational root theorem. Yes, there is a short detour to algebra today, but before we go to question number 17, I thought it's better to explain what is rational root theorem. It will be a very quick explanation. I'm not going to prove it. That's not the scope of this video. For the detailed proof, we will do a detailed video on algebra later. But for now, I'll just do the statement of the theorem and do two examples on rational root theorem. Okay? First, let us see what is rational root theorem. Suppose there is a polynomial p of n, where n is the degree of the polynomial, and the polynomial is of the form if we have a polynomial Pn which is of the form an x power n plus an minus 1 x power n minus 1 plus an minus 2 x power n minus 2 plus and so on plus a1x plus a0. And if we have a polynomial like this where ai, that is an minus 1, an minus 2, etc., a1 and a0 are the coefficients of the polynomial. And if an minus 1, an minus 2, and so on, a1 and a0 are all integers, and a0 and an are not equal to 0, then all possible rational roots of this polynomial are of the form p divided by q, where p is the list of all possible integer factors of a0, the constant term, and q is the list of all possible integer factors of an, the coefficient of the highest exponent. And p and q will have to satisfy another condition. P and Q have to be relatively prime. That is, when you are drawing the list of P divided by Q, you'll have to reduce P by Q to its lowest term. May sound a little confusing now. Let me do a couple of examples. You will be able to understand very easily. Okay, first, let me write down what I have said till now clearly, then we will go to the examples. Okay, so this is the statement of the rational group theorem. What does it say? It says that if we have a polynomial like this and ai, which is an minus 1, an minus 2 up to a1, are coefficients of the polynomial pn, and a0 is the constant term, and ai is set of all integers. That is, all these coefficients have to be integers. That is, it can be 0, it can be 1, 2, 3, 4, or minus 1, minus 2, minus 3, 4, etc. But an and a0 are not equal to 0. That is, an, the coefficient of the highest exponent, and a0 cannot be 0. That is, an comma a0 is not equal to 0. Then all possible, I have underlined possible. That means this theorem is not about finding the roots of the polynomial. This theorem only says all possible rational roots have to satisfy this condition, and if this condition is not satisfied, the roots are not rational. That's what it says. All possible rational roots of Pn are of the form P divided by Q, where P is all integer factors of a0 and Q is all integer factors of an, and P and Q are relatively prime. Okay, as I said before, we will do two examples. You'll be able to understand very easily. Okay.
I hold a master's degree in physics. I am an avid amateur astronomer. I also make educational YouTube videos, some of which you can see here. Thank you.